Today we're going to talk about conducting a linear regression test. So the regression model means the mean response, mu sub y, average of your y's, population y's, has a straight line relationship in regards to x, denoted by mu sub y equals alpha plus beta x, where slope beta and intercept alpha are unknown parameters. And for any fixed value of x, the response y varies according to a normal distribution, and repeated responses of y are independent of each other. Standard deviation of y, sigma y, is the same for all values of x, and sigma y is also an unknown parameter. Okay, suppose we look at a part of a population of adult women, and all of these women are 64 inches tall. Notice they have different weights. So what distribution does their weight have? Well, if we make a normal probability plot, it would look like as such. So we use y hat, the predicted y's, equals a plus bx to estimate your population mean of the y's to equal alpha plus beta x. So the slope b of the least squares regression line is an unbiased estimator of the true slope beta. So remember, unbiased means that your sample matches the population. The intercept a of the least squares regression line is an unbiased estimator of the true intercept alpha. And the standard error s is an unbiased estimator of the true standard deviation of y, sigma y. So standard error has this big long formula, big square root of summation of your residual squared, your actual y minus predicted y hat squared, all that divided by your sample size minus 2. Again, you can locate these on your AP formula sheet. Reminder that your degrees of freedom for your linear regression test is n minus 2. So your sample size minus 2 because you have x variation and y variation. So you have 2 different variables of variation. Okay, so say we have a graph of our height versus our weight. So suppose we took many samples of the same size from this population and we calculated the least squares regression line for each. So using the slope from each of these least squares regression lines, we can create a sampling distribution for the slope of the true least squares regression line. So what we're going to do here is we're just going to graph the slopes, the slope of each of those lines, least to greatest. So what shape will this distribution have? It should be approximately normal. What is the mean of the sampling distribution? Your population mean of B should equal beta. What is the standard deviation of the sampling distribution? That is this big long formula. So again, all these formulas are located on your AP formula sheet. Make sure to find where those are located. So assumptions for inference on slope. It first needs to be linear. Examine the scatter plot to check that the overall pattern is roughly linear. Look for curved patterns in the residual plot. Check to see that the residual center on the residual equals 0 line at each x value in the residual plot. You need to see is it independent. Look at how the data were produced. Random sampling and random assignment help ensure the independence of individual observations. Sampling is done without replacement. Remember to check that the population is at least 10 times as large as the sample. Make a stem plot, a histogram, or a normal probability plot of the residuals, and check for clear skewness or other major departures from normality. We need equal variance, so look at the scatter of the residuals. Again, we should see no pattern in residuals above and below the residual line. The amount of scatter should be roughly the same from the smallest to the largest x value, half above, half below, and no pattern. And as always, we need randomness. See if the data was produced by a random sample or a randomized experiment. So acronym to help you remember: LINER. L, linear. Check the graph. I, is it independent? N, is it approximately normal? Check the graph. E, equal variance, and R, random. So supposedly squares regression line has a horizontal line. Would height be useful in predicting weight? Well, what is the slope of the horizontal line? The slope of a horizontal line is 0, so a slope of 0 means that there is no relationship between x and y, which makes sense if our height is all the same. So our hypothesis when we're doing a linear regression test is always we're testing, is the slope 0, meaning that there is no relationship between x and y. Now this implies that there is no relationship between x and y, or that x should not be used to predict y. But what would the slope equal if there were a perfect relationship between x and y? Well, then that slope would equal 1. So be sure to define your slope in regards to the objects that you're talking about. So while null will always be that your slope equals 0, your alternative could be that it's greater, that it's less than, or not equal, all depending on the sentence in the problem. So formulas for your linear regression test and confidence interval. As always, your confidence interval is your statistic, which for linreg will always be from a set of data values, which we can call B. Your critical value, because it's sample slope, critical value will always be a t-value because you will be using from data. Time standard deviation of your statistic, which is S B sub 1. Again, all formulas are on your AP formula sheet. Yay, calculator does the work for us by inputting our data into list and spreadsheets and then going to menu, statistics, confidence interval, t-interval, linreg. So what if we want to do a hypothesis test to get that test statistic? Again, it is always a t-test because we're using actual data values. B minus B beta divided by S sub B sub 1. And again, yay, the calculator does the work for us by hitting menu, statistics, test, and linear regression t-test. Reminder, your degrees of freedom again is n minus 2 because you have x and y variability. So again, these formulas are on your AP formula sheet. Just make sure to locate where they are. Okay, so let's look at an example. We have, it's difficult to accurately determine a person's body fat percentage without immersing him or her in water. So researchers hoping to find ways to make a good estimate immersed 20 male subjects and then measured their weights. So what we need to do is find the least squares regression line, the correlation coefficient, and the coefficient of determination. So to do that, we're going to need to utilize the calculator. Okay, so first we need to input our data values into our calculator under list and spreadsheets. Make sure to title your columns. We're going to title it, I will title it weight, body fat. So that left column, again, type in your data values. You double check your values. Again, calculator can only compute what you enter in correctly. Okay, and then put in the body fat percentage. I caught one, always good to double check as I found my mistake there. Again, calculator can only input based on the values that you input in. So that you have correct calculations. Okay, and if we're needing to find the least squares regression line, we make sure that we have one cell highlighted, go to menu, statistics, stat calculations, and we want linear regression, mx plus b. What is my x list? I called it weight. What is my y list? I called it BF. Hit enter. And again, you should have output here. So notice my slope is 0.249. Notice my y-intercept is negative 27. I have r squared and I have r. Okay, so notice, how do we write that as an actual equation? My body fat, or y hat, would equal negative 27.376 plus our slope of 0.25 times the weight, or times x. Again, if you're using a y hat and x, make sure to find x equals weight. Y hat would equal body fat. Otherwise, you need to actually write it out like the equation is shown here. Notice our correlation coefficient is 0.697 for r, and r squared coefficient of determination is 0.485. So explain the meaning of the slope in the context of the problem. Well, how do we interpret slope? There is approximately, what is the slope? 0.25, it is given as a percentage in the data table. Increase in, because it's positive, in body fat for every pound increase in weight. So explain the meaning of the coefficient of determination in context. Coefficient of determination is r squared. And again, we say approximately, change it to a decimal. 48.5% of the variation in body fat can be explained by the regression of body fat on weight. So estimate alpha, beta, and sigma. Okay, if you actually perform the lin-reg test on your calculator, calculator will actually give you these values. Again, on your AP formula sheet, I snipped out the part where it says sampling distributions for simple linear regression. So these are formulas if you want to hand calculate, but I would run the linear regression test on your calculator, and you can actually find alpha, beta, and a sigma. So again, alpha is already, just from the problem, your y-intercept negative 27.376. Beta, again, is your slope of your regression line, so 0.25. And again, sigma you can find on the calculator using your least squares regression line test. Again, or if you want to use the formula, but you'll get 7.049. So create a scatter plot and a residual plot for the data. Again, from your calculator, you can hit menu, quick graph, scatter plot, change it if it defaults otherwise. But body fat scatter plot would look like this with weight and body fat. And again, once you have the scatter plot, if with the least squares regression line, you can then plot the residual plot. And again, reminder that a residual plot is just zoop, moving that least squares regression line horizontal. And if it is a true best fit least squares regression line, again, I should have random, no pattern in my residual plot, which I do have. So, is there sufficient evidence that weight can be used to predict body fat? Well, is there sufficient evidence means that we need to conduct a full test. So to conduct a full test, we first start with assumptions. I need a simple random sample of males, check. I need the residual plot to be randomly scattered. I just check that, check. Since the points are evenly spaced out across the least squares regression line on the scatter plot, sigma y is approximately equal for all weights, values of weights. And since the box plot of residual is approximately symmetrical, the responses are approximately normally distributed. So what would our null and our alternative be? Again, we are seeing is our slope beta equal to 0, where B is the true slope of the least squares regression line of weight and body weight. Our alternative is that is it not equal. Okay, so your data values are already in the calculator. Again, difference here is that we're no longer doing least squares regression line, we're doing the least squares regression line test. So make sure that one of your data cells is highlighted. Go to menu, statistics, stat test. Again, menu, statistics, stat test, again, and we are going to lin reg t test. So what is my X list? I called it weight. What is my Y list? I called it body fat. Again, we're testing against not equal to. Do I want to override? Yes, I want to override. And notice I can write down, I can name the test if I'm using calculator, linear reg t test. I can write down my test statistic of 4.11 t equals. I can write my p-value of 0.00643. Notice here, if you just see 6.43, it says times e to the negative 4. That means it is scientific notation. Scientific notation, so you got to move that decimal to the left 4 times, which means we have 3 zeros, so 0.0006. Degrees of freedom is 18. And notice it still provides you your least squares regression line equation as well with your AB. Okay, so again, showing all work. You either name the test, calc, lin, reg, t test, put down all of the output. Again, if you're hand calculating t, you'd get 0.25 minus 0 divided by 0.0607. So our p-value is 0.006, our degrees of freedom is 18, our alpha, unless stated otherwise, is 0.05. So is p low or is p high? P is very low. So since p is less than alpha, I reject the null. There is sufficient evidence to suggest that weight can be used to predict body fat. Which again, logically makes sense. Typically, the more weight you have, probably the higher percent body fat. Again, always exceptions to the rule on people that work out more often. So what if we need to give a 95% confidence interval for the true slope? Again, always same thing with confidence intervals. We need to state our same assumptions. We've already said SRS check. We have a residual plot that is randomly scattered to check for linearity. Points are evenly spaced, and the box plot of the residual is approximately symmetrical, so that denotes it as approximately normal. Again, make sure to draw a quick sketch of the graphs. A calculator can help you with those. We can use our calculator using confidence interval, menu statistics confidence interval, linear reg t interval. Again, if you want to calculate, the formula is on your AP formula sheet. You can do so as such. We'll get this interval, and if we state our sentence, we are 95% confident that the true slope of the least squares regression line of what are we talking about? Weight and body fat lies in the interval 0.12 and 0.38. So again, if you're finding a confidence interval, don't forget assumptions. So here's a computer generated result from the data. So let's remind you how we can write the least squares regression line from computer generated output. So what are the degrees of freedom? Well, we can check sample size -2, that would be 18 degrees of freedom. R squared is what's called your correlation coefficient. And again, make sure to change it back to a It's normally written as a decimal, 0.4383, and you can change it to a percent. Little s is your standard deviation. What do the estimate, these numbers represent? They represent the slope and the y-intercept. So this helps you get your y hat equation. So y hat here would equal 0.249x plus minus 0.27.37. So again, intercept is your y-intercept. The one not labeled intercept is your slope. 0.249 is slope. Standard error, what is circled is standard error, 0.06. And that concludes linear regression test.